Okay. All right, so today I'm going to be going over determinants. Okay. All right. And so to start things off, I wanted to recall this formula for the inverse of a 2x2 matrix. So most recently, I used it a little bit last time when I was talking about projections and least squares. And so I made a comment, and you've maybe heard from your professors as well, that this number that's in the denominator in the formula, so AD minus BC, so that number is called the determinant of the matrix ABCD. Here I'm introducing some new notation where to denote the determinant of a matrix, you see that we can use like a vertical bars on the sides as opposed to brackets. And whenever you see someone using vertical bars on the side, that would denote the determinant of the matrix, okay? So just as like a small example, here we have a 2x2 matrix. So if we use this formula for computing its determinant, it's A times D minus B times C. So you'll get 12 plus 2 for a total of 14, okay? All right, so today I'm going to be talking about what is the significance of this number that we get when we compute the determinant. And then we're also going to learn how to compute the determinant of larger matrices as well, okay? Okay. So let me start by talking a little bit about the significance of the determinant. So like what does that number actually represent, or what does it calculate? So here, let me kind of draw a picture. And I'll use the example that I have up here. So in this matrix, we have, in the columns, we have two vectors. We have in the first column, the vector 3, 1, which I'm going to draw in this picture. Vector 3, 1 is going to look something like that. So that's vector 3, 1. And then here we've got another vector in the second column, negative 2, 4. So let me draw that vector in this picture as well right now. So let's say that's negative 2, and that's 4. Okay. All right. So we have these two vectors. So these were the columns. Okay. Okay, all right. So then these were the columns of our matrix up here. Now these two vectors, they create a parallelogram, which I'm kind of drawing in the picture. And so it actually turns out that the determinant of this matrix, it's actually computing the area of this parallelogram. With edges determined by the two vectors 3, 1 and negative 2, 4. Okay. All right. So then more generally, the determinant for a 2x2 matrix is going to return the area of the parallelogram formed by the two columns of the matrix. Okay. All right, sorry, I briefly lost my train of thought, but I'm good. Now, determinant, however, when you're computing the determinant of a matrix, sometimes you get a negative number when you compute it. So it's maybe not quite correct to say that it gives you the area. So it's maybe more appropriate to say it gives you plus or minus the area instead. Okay. And I want to talk a little bit about what the sign represents as well. So when the determinant is positive or negative, what is that telling us about the two vectors? Okay. So the sign of the determinant, it kind of tells you what the orientation of your two vectors was. And I'll talk a little bit about what I mean by the orientation. Okay. So here I'm going to draw two pictures. So here's one picture with two vectors u and v. And then I'm just going to draw another picture here. Like that. Okay. Okay, so in this first picture, looking at these two vectors u and v, so notice that in order to get from u to v, there's kind of two ways we can imagine doing that. So we can kind of imagine traversing in a sort of counterclockwise direction, or we can also imagine traversing in this would be a clockwise direction instead. Okay. Now in this picture, the shorter distance though is if we go in the counterclockwise direction. So these two vectors we'll say has a sort of a counterclockwise orientation to them. But in contrast, if we look at this picture, see here, did I set this picture up correctly? Well, I guess I was thinking like this rather. But okay, let me draw a different picture. I think that would be better. Let's set it up like this. I'll kind of make it look almost the same. Okay. Okay, so then in this picture, if I start with vector u, again, we can imagine moving either clockwise or counterclockwise to get to v. And this picture, however, the shorter distance is going to be if you move in the clockwise direction. So that kind of gives the vectors uv a sort of opposite clockwise orientation instead. So when your two vectors have a counterclockwise orientation, the determinant of the matrix, with columns u and v, is going to be positive. Whereas in this picture where the shorter distance from u to v is the clockwise distance, the determinant of u and v is going to end up being negative instead. Okay. All right. So that's just kind of a brief idea of what the sign of the determinant is telling you. It's telling you the orientation of your two vectors. Okay. And so I'll be talking about how to compute the determinant in just a bit. And we'll talk about how to get the determinant of larger matrices as well. But if I just talk about 3x3 matrices real quick. So let's say you have 3 vectors in R3. And let's say we put them into a matrix A as the columns. So column 1 is U, column 2 is V, and column 3 is W. Okay. So these three vectors, if you draw them, they'll form sort of a three-dimensional version of a parallelogram, which we refer to as a parallelepiped. I'll try to draw a picture of it here. Okay, that's pretty good. Okay. So let's say one of these vectors is u, the other was v, and the other was w. So in this case, the determinant of the matrix A, similarly in the two-dimensional case, here it gives you plus or minus the volume of this parallelepiped, okay? And again, the plus or minus sign corresponds to the orientation. So positive sign means that the three vectors have what we call a right-handed orientation. And so positive means it's got a right-handed orientation. And then if it's a negative sign, then it has what we call a left-handed orientation instead. And so maybe for those of you who have taken physics, I know in physics they often talk about like right-hand rules for a lot of the formulas. So that's kind of related to here when we're talking about a right-handed orientation versus left-handed orientation. So that's what the sign corresponds to. It corresponds to the orientation of your vectors, okay? Okay, so now that we've talked a little bit about some of the, well, yeah, that's right, yeah. Let me think in this picture, so I guess like if you take your index finger, point it in the direction of the first vector u, middle finger point it in the direction of the second vector v, your thumb, if your right thumb points in the direction of the third vector, that's a right-handed orientation. If your right thumb points in the opposite direction, then it's a left-handed orientation instead. In my picture, the way that I'm seeing it with my right hand right now, it seems to be a right-handed orientation. Okay. So yeah, if I try to put my index finger in the direction of U, middle for V, my thumb is kind of pointing more upwards, if you will, which is how I try to draw W. This is pointing a little bit more upwards than down. Okay. All right. So the determinant, because of this kind of like geometric information that it contains, it's pretty important when you go into multivariable calculus. So that comes up in like your change of variables formula when you're doing integration, and it comes up in like other places as well. I would say mostly related to integration for multivariable calculus. Okay. Okay. Now I'm going to move on to talking about some of the properties of determinant and how to compute the determinant of a matrix as well. There's quite a few ways of computing the determinant of a matrix. They're all somewhat tedious. Can't be avoided, I want to say. Although for like 2x2 and 3x3 matrices, it's not bad at all. Okay. Okay. So before we can give a formula for the determinant, we need to go over some of the properties of it first. Okay. Okay. So the first property of the determinant is that it has sort of like a distributive or additive property to it. So if you have the determinant of, well, let's do it like this. So for now, let me just stick in 2 dimensions for now. Okay, so let's say we have 3 vectors u, v, w, and r2. Okay, so one property that I want to mention is this sort of additive or distributive property, where if you want the determinant of the matrix whose first column is u and whose second column is v plus w, okay, the determinant of this matrix will be equal to the determinant of u, v, and then plus the determinant of u, w. Okay. And here you can, it kind of looks like if you were like multiplying the u times v plus w, you could distribute the u and get like u times v plus u times w. That's kind of what this formula kind of looks like, okay? Likewise, if you have a sum but in the first column instead, so the first column is u plus v and the second column is w. Again, you can kind of distribute the w, if you will. So it's kind of like u plus v times w is u times w, and then plus v times w. Okay. All right. Another property is if you, oh, and so a sort of intuitive way of thinking about this property. So you can kind of think of like each of these vectors as representing the base or the height of like the parallelogram that they form. So if you think of like v and w as representing the height, here we're kind of saying like if you do like the base and then let's say the height is the sum of the heights of like v and w. So when you compute the area by doing like base times height, it's like the same as adding the areas of the 2 parallelograms determined by u and v and u and w. So that's kind of the idea of that property there. Okay. And then this second one is kind of similar. So it's like the height determined by v plus w is like the same as the height determined by v plus the height determined by w is the idea. Okay. There's another property involving scalar multiplication. All right, so the first property is kind of involving vector addition. Second property involves vector multiplication. So if you are scaling one of the columns by some number k, that will scale the overall determinant by k as well. Okay. And that's true whether you're scaling the second column or whether you're scaling the first column. Okay. So again, if you're kind of thinking in terms of area as a base times a height, here it's like you scale the height by a factor of k. So that scales the entire area by k as well. Okay. And likewise, if you scale the base by a factor of k, that also scales the area by k. That's the idea of the second property. Okay. Third property is if you swap the columns, the determinant will change sign. So like the determinant of the matrix with columns U, V will be the opposite of the determinant of the matrix with columns V and U, okay, with the columns swapped. And so the idea of this is if the vectors U and V have a, in this picture, they have a counterclockwise orientation. Okay. But if I start with V first and then go to U, then they'll have a clockwise orientation instead. So whenever you swap the columns, it's like the orientation flips. That's the idea of that, okay? And then one more property that I'll mention is the determinant of the identity matrix should be equal to 1. So thinking just in terms of orientation and area. So of course, the two columns of the identity matrix, they form like a unit square. So the area should be equal to 1. And then these vectors, they naturally have a counterclockwise orientation to them as well. So the determinant should be positive instead of negative, okay? All right. Yes. Yeah, so it's like which one is like the shorter path, I guess, to get from the first vector to the second one, okay? Okay. Now I phrased all these properties for like vectors in R2. So like this is all for like a 2x2 matrices specifically then, because here the first column would have 2 components. The second column would also have 2 components in it, okay? But all these properties are also going to be true for like any dimension as well. Okay. So I won't rewrite all of them, but maybe just looking at the first property. So it's a little bit harder to write these properties down when you have like n columns in it. But the first property, I would maybe write it something like this. So in this case, like you have like an n by n matrix, so it'll be n columns. So let's say the first column I'll denote by as like a vector v1. Let's say the second column is v2. Let's say in the ith column, we have a sum of 2 vectors like vi plus wi. And then the last column, we'll call it vn. Okay. So in this case, you can kind of like distribute this as well. And it'll be equal to the determinant of the matrix with columns v1, vi in the ith column, vn, and then like plus determinant, and then again like v1, v2, but here in the ith column you'll have a wi instead. Okay. So this is what that first property would look like for like a general n by n matrix. Okay. All right. So then the second property is if you scale one of the columns by k, the determinant will get scaled by k as well. Okay. Here, if you swap 2 columns, the determinant changes sign, so that still holds for n by n matrices. And then lastly, the determinant of the n by n identity matrix will also be positive 1. The idea being like the columns of the identity matrix will still kind of give you like a unit cube, if you will, even in like n dimensions. And I guess we sort of defined the orientation of that to be like the positive orientation. Okay. All right. So these properties are all kind of motivated by sort of the geometric property of the determinant. So I talked about how like this property comes from like the idea like if the height is the sum of these two vectors, the overall area is the sum of these two areas with heights like v and w. Okay. Likewise, this property was kind of similar. Scaling one of the edges will scale the area by that same amount. So all these properties are motivated purely by the like geometric properties of the determinant. And then with these properties, we can actually derive the formula, or at least one of the formulas for computing determinant. Okay. This formula that I'm about to derive, this is the one that they're calling the big formula. Okay. So I think that's maybe terminology in your textbook, but I think your professors are using that terminology as well. So there's like one question in your homework assignment that's like, use the big formula to calculate the determinant, okay? So that's what I'm gonna go over right now. I'll show you how it works for the 2x2 case, because that's kind of small enough as to where it's not that big. Yeah. Huh? So I'll cover the 2x2 case. I'll kind of like do the computations to see how it works. But then I'll just give you like the general formula for larger matrices, and then we'll try to look at an example as well, okay? Okay, so here's the idea. We have, let's say we're trying to compute the determinant of a 2x2 matrix, A, B, C, D, as usual. Okay. So the first column, we have this vector AC. And that first column, I'm going to rewrite it as a linear combination where vector AC is A times 1, 0 plus C times 0, 1. Likewise, the second column, vector BD, I'll also rewrite it as a linear combination. BD is B times 1, 0 plus D times 0, 1. Okay? And maybe just to avoid too many brackets, maybe I'll do big parentheses instead. Okay. All right. Don't be too concerned about like parentheses and brackets. Okay. So let's see here. Next. Because of the sort of additive or distributive property that we talked about up here, that means that when you have an expression like this, you can kind of like FOIL this expression out, okay? So think of it as like this times this. So if you were to FOIL it, you'd have like this times this first. And I'll use the second property as well, where I can kind of take any scalars on the inside and factor them out to the front. So here, when I kind of FOIL this, looking at the first two terms, we have A, B, and then we have 1, 0 and 1, 0 again. Next we have, if I continue sort of foiling, we'll have A, D, and then we also have a 1, 0, and 0, 1. So 1, 0, 0, 1. And then next, if I kind of multiply, if you will, the C. So, whoops. This one and this one will give me BC. And then we're going to get a 0, 1 followed by 1, 0. And then finally, at the end, we're going to get CD. And then it's a 0, 1, and 0, 1 again. Okay. So kind of described it as foiling, sort of. Okay. All right. Okay. Now, this matrix here has a determinant of 0. Okay. One way you can look at it is that, if you just kind of visualize it, vector 1, 0 with vector 1, 0, this would form like a parallelogram of area 0, because it's just like a line, if you will, or an arrow. You can also look at it as a consequence of the dirt property, though. So I'll make a quick comment on that. So this dirt property also says that if you have a matrix with identical columns, okay. Well, so this property says if I swap the columns, I'll pick up a minus sign, right? But here, if I swap these two columns, I still get the same matrix, because it has the same columns. So here it's like the determinant is equal to the negative of itself. And the only number that is equal to the negative of itself is the number identical to be 0. Okay. All right. So whether you look at it as a consequence of the dirt property or just the idea that the area that these two vectors form is 0, we can say that's going to be 0. And then likewise, this one down here will also be 0, because the vectors 0, 1, and 0, 1. Again, they don't create any parallelogram with any area. Okay. Likewise, we know that the determinant of the identity matrix should be 1. So this is going to be like AD times 1. And then here, this is the identity matrix, but with the two columns swapped. Okay. So because the two columns have been swapped, that adds a negative sign to the determinant. So instead of determinant being +1, the determinant of that matrix is -1. And that's how we get that formula for a 2x2 that we've talked about earlier, AD minus BC. Okay. All right. So you can also do something similar for the general n by n case. I'm definitely not going to work that out, but just kind of a brief comment on that. So for like an n by n matrix, you could take each of the columns and write it as a linear combination of like these vectors. So like the columns of the n by n identity matrix in that case. You could kind of FOIL all of it out, but it would be like a massive thing to FOIL in general. But any of the terms that have like a repetition will zero out. And then all the other terms, you can kind of get like ±1, depending on the number of swaps needed to like get to the identity matrix. And you'll get to this sort of big formula at the end. Yes. This one. Yep. Here. Okay. Not really a multiplication. Yeah, so here I put a comma maybe just to distinguish them a little bit more. But there's like this is representing the first column of the matrix. This is representing the second column of the matrix. Yeah, okay. Yes, Yep. Exactly, that's right, yeah. So when we talked about the 2 by 2 inverse formula, in my review, I think I kind of very briefly mentioned this is called the determinant, but I didn't say much else about it, right? And then, yeah, your professors may have also mentioned like, oh, this is called the determinant. We'll talk about it later. So, yeah, so that's right. Yeah, that's right. Yeah. Okay. Uh, so I'm not going to work out the whole process, but to give the big formula for the n by n case. So I'll introduce like a little bit of notation, which I'll kind of explain because we need the notation to write out the formula. Okay. Okay. So, and I'm going to try to use notation that at least one of the classes seem to be using. So I'm going to let S denote this kind of like list of numbers S1 through Sn. And here the numbers S1 through Sn, they're going to be like a reordering or a permutation. Of the numbers 1 through n. Okay. So just take the numbers 1 through n and imagine just like shuffling them around into a different ordering. That's what this is representing. Okay. Now, with each permutation, we can associate with it something called the sign of the permutation. Okay. So the sign of a permutation is defined to be either +1 or -1. Okay. Um, say that again. Yeah, that's right. Yeah, it's always 1 or -1. So what the sign of a permutation refers to is it refers to the like number of swaps that you need to get it back into like the natural order. So if it requires like an even number of swaps to change it back to the natural order, then the sign will be +1. And then if it's instead it requires like an odd number of swaps to get it back into this order, then we'll say the sign is -1. Okay. So then if you kind of do this process but for like a general n by n matrix, it will turn out that the determinant of A, you'll get this formula where it'll be a summation over all permutations S. And you'll be adding or summing the sign of S times AS11, AS22, etc. times, and then at the end, ASNN. Okay. So let's talk about this formula a bit, and then we'll also use it to get the determinant of, I'll do a 3 by 3 example. Okay. So here I'm using notation that I guess we've kind of seen before. So Aij denotes like the entry in like the ith row in the jth column of A. So this is like this A S1 1. That's like the entry that was in the S1th row in the first column. AS22, that's like the entry in the S2 row in the second column, etc. Okay. So we're taking certain entries of the matrix, multiplying them together, and then we're multiplying by plus or minus 1, depending on the permutation S. And we do this for all permutations, so all reorderings of the numbers 1 through n. Okay. All right. Now I'll make a quick comment, and then I'll do an example with the 3x3 case. So sometimes people, depending on how they describe, like maybe like how they explain things at the beginning, you'll also see the formula written like this. Where the difference is the indices, as you see, they've kind of been swapped, okay, in all of them. So I prefer to set it up this way because I'm thinking in terms of like the columns of A. So when I was like describing determinants, I was always looking at like the columns of the matrix, okay? But some people will maybe like look at the rows instead, so they might set it up like this. Both formulas give the same answer, so it doesn't like ultimately matter which formula you use. But I just wanted to highlight that some people, you'll see some people use this kind of version of the formula instead. Okay. All right. Okay, so let's see how this big formula would work to compute the determinant of a 3x3 matrix. Yes. Mm-hmm. Yeah, so like so here the columns like 1 through n are kind of fixed, if you will. So like this is always an entry in the first column. This is always an entry in the second column. But here they kind of flipped it where like this is like an entry in the first row. Yeah, this is an entry in the second row and so forth, okay? Yeah. So it happens that they both give the same answer though. So I'll talk about it later, but there's a property that determinant of A transpose is the same as determinant of A. And that kind of reflects the fact that these two give you the same result, okay? All right. Okay, let's see here. So I wanted to do a 3x3 example. Oh. Actually, I'm going to make 2 more comments real quick. So, and in the big formula, I said that this is a summation over all of the permutations, so all of like the reorderings of 1 through n. So it's worth noting, like how many permutations are there? So the number of permutations of 1 through n happens to be equal to n factorial, okay? So n factorial grows pretty large pretty quickly. And that's kind of one reason why they refer to this as like the big formula. So as an example, if n is equal to 4, 4 factorial, remember factorial is like 4 times 3 times 2 all the way to 1. So when n is 4, there's going to be 24 permutations of the numbers 1 through 4. So this big formula would have like 24 terms being added together for like the n equals 4 case, all right? So already when n equals 4, it's kind of like a little bit too big to really be using to compute the determinant. Okay. But I think it's worth noting, so number of permutations is n factorial, and half of the permutations are going to be even permutations, so the sign will be +1. The other half will be odd permutations where the sign will be -1 instead, okay? Okay. So that was just a couple more comments, and now let's do a 3x3 example. Okay. So let's say we have this matrix A. So it's 1, -2, 0, 0, 3, 2, 2, 1, -1. And let's say we'll want to compute the determinant using the big formula, okay? Okay. So first thing that I'll do is I'll kind of list out all the different permutations of the numbers 1, 2, and 3. Okay. Okay. So here we have like sort of the natural ordering of the numbers. So that's kind of one permutation. And then I'm just gonna kind of imagine if I keep swapping the numbers around to get different permutations. I can, I guess, like swap the 2 and the 3. So that's another permutation. I can maybe start with 2, and then let's do 1, 3. And then let's swap the 1 and the 3. And then I can start with 3, and then we can maybe go 1, 2, or 2, 1. Okay. Now there should be a total of 3 factorial or 6 permutations. And so here, I've already listed all 6 of them out then, okay? But like, if you had to do this for the n equals 4 case, there would be 24 permutations total then. So you'd have to maybe think about like all the permutations. And if you see that you don't have 24 of them, you've maybe missed some of them, okay? All right. Yeah. So these are all the permutations of 1, 2, 3. Now I want to think about what's the sign of each of these permutations, okay? So here, so the sign is plus or minus 1, depending on if you need an even or an odd number of swaps to put it back into like the natural order. This one requires 0 swaps. It's already in the natural order. 0 is an even number, so its sign is +1. Okay. Right, that's right, yeah. Yep. For this one, if we do 1 swap the 2 and the 3, that puts it back in the natural order. So it needs an odd number of swaps. So this one has a sign of -1, okay? For this one, if we swap the 1 and the 2, that puts it in the natural order. This one, I would need to do 2 swaps. So maybe swap the 1 and the 3, and then swap the 2 with the 1 after that. So this has a positive sign. Let's see, this one, I think requires 2 swaps as well. So this one has a positive sign. This one, if you just swap the 1 and the 3, that will put it in the natural order. So it requires 1 swap, so its sign is -1, okay? Yes. Yeah, so if you need an even number of swaps, its sign will be +1. And if you need an odd number of swaps, its sign will be -1, okay? Okay. So then, according to the big formula, the determinant of this matrix A, it will be equal to, so I'm going to take each of these permutations, starting with the first one, 1, 2, 3. So we're going to have a 1, 1, A22, A33. Okay. For the second permutation, 132. So the permutation will give you like the first subscript. Okay. At least how I'm doing it up here. So the permutation gives you like the first subscript. And then the second subscript is always like 1, 2, 3. Okay. All right. So the next one is 132. So we're going to have 1, 3, 2, and then the second one is always 1, 2, 3. And this one was an odd permutation, so we're going to be subtracting those. Okay. Next we have a 2, 1, 3, and it's going to be minus. So 2, 1, 3, 1, 2, 3. Next is 2, 3, 1. It'll be plus. Yeah. Next one that I have here is plus. It's 3, 1, 2, and then 1, 2, 3. And then the last one is minus. And we have 3, 2, 1, 1, 2, 3. Okay. Okay. So this is the big formula completely written out. Yeah, it'll always be 1. Yeah, so plus or minus. Okay. Yep. Let's see here. Just swap the 1 and the 2. Oh, that one. This one. Okay. Oh yeah. How is it even? Right. So swap the 1 and the 3 first, maybe, to get like 2, 1, 3. Yeah, and then swap the. Yeah, that's right. Yeah. That's right. Yeah, that's right. Okay. All right. Good. So then now we need to take each of these entries from A and multiply them together. Okay. So this one multiplies the diagonal entries 1, 1, 2, 2, 3, 3. So it's going to be like 1 times 3 times -1 for this. Okay. Let's see here we have A11, which is 1. A32, third row, second column is 2. A23, second row, third column, that's a 1. Let's see here, this one, A21 is -2. A12 is 0. So this one's already 0 because you're multiplying by 0 there. Okay. So I'll just continue to the next one. A21 is -2. A32 is 2. A13 is 2. A31 is 0. So that's going to 0 out when you multiply. And then likewise on this last one, A31 was 0. So when you multiply it, then it's going to be 0 again. Okay. So here we're going to get -3, -2, and -8 for a final answer of -13. Okay. Yep. Yep. Yeah, that's right. Yeah, you should get the same answer. That's right. Yeah. Okay. Let's see here. What would happen is for the second way, each of these permutations would give you the second subscript now instead of the first. That's what would happen. Okay, all right, okay. That's right, yeah, that's right, okay. Okay, let's see here. So then if you were to draw the three vectors like 1, -2, 0, 0, 3, 2, and 2, 1, -1, if you would like imagine or visualize them in R3, they would form a parallelepiped whose volume was 13. And they would have a left-handed orientation because of the negative sign. Okay, all right. Okay. Mm-hmm. That's right, yeah, that's what you'd be getting, yeah. Okay. So we'll talk about some more like efficient ways of computing the determinant now, okay? So using the big formula is quite tedious. You would pretty much never use it unless you were told to use it, basically, okay? Okay. So the most efficient way of computing the determinant, especially for larger matrices, is using row operations or column operations. Okay. So first, let me talk about how performing row operations on a matrix will affect its determinant. Okay. So there are three types of row operations that you can perform. At least we classify them into like these three types. So you can multiply a row by a scalar. So if you multiply a row by a number k, that will also scale the determinant by a factor of k as well, okay? Another type of row operation that you had was swapping two rows. So when you swap two rows, the determinant will change sign. We kind of talked about that earlier, although we talked about it for columns. Okay. Now the operation that you tend to do the most of, like when you're doing like your elimination, so you like add a multiple of a row to another row, add or subtract. So this last type of row operation, it actually does not change the determinant at all. Okay. All right. So I'll illustrate with an example of like computing the determinant of a matrix by performing operations on it. Here I phrased all of these in terms of row operations because that's what we tend to do in all of our problems. Technically, these are also true for columns as well. So like swapping two columns changes the sign. We already saw that earlier. Multiplying a column by a scalar scales it by that amount. And adding a multiple of a column to another column doesn't change it. Okay. Now, one fact that I need to mention real quick before I get to my example. I'm not really going to prove it, but it's something that you can figure out using the big formula, not too difficultly, I guess. But there's a fact I'm going to mention here that the determinant of a triangular matrix, whether it's an upper triangular or lower triangular, or even diagonal, which would be, so diagonal matrices are just both upper and lower then, okay? So one or the other, but the determinant of a triangular matrix turns out to be equal to the product of its diagonal entries. Okay. So one way to find the determinant is to reduce a matrix to a triangular matrix, where then you can easily calculate the determinant of that triangular matrix. And then you can figure out the determinant of the original by seeing how the row operations were affecting its determinant, okay? So I'll do an example now to illustrate that. So let's say we have this matrix A. And I'm going to compute the determinant by reducing it to a triangular matrix, okay? I'll reduce it to like the usual upper triangular form. Okay. So I'll do a couple of things to do that. So maybe first, I think I would like to have a 1 as a pivot, so I might swap rows first, okay? So let's say I'm going to swap like row 1 and row 2 right now. I'm going to swap the two of them. And we'll think about the determinants later, but right now let's just focus on the elimination. So first I did a row swap, okay? And now I'm going to use this one as a pivot to eliminate everything underneath it. So I'll do like row 2 minus 3, row 1, row 3 plus row 1. Okay. This would be 1 plus 3 is 4. 2 minus 1 is 1. Okay. Now here you could just do maybe another elimination, but let's say that I want to divide the second row by 2 because I see that would work kind of nicely. Let's say I'll divide it by -2 to get like a positive 1 as a pivot. So let's say I multiply row 2 by -1/2. Okay. And then I'll just do one more elimination, row 3 minus 3, row 2. Okay. And that's going to give me 1 plus 6, so it'll be 7 at the end. Okay. All right. All right, so down here, I'm going to sort of keep track of what was at the determinant of each of these matrices. Okay. So originally starting with A, so determinant of this, we don't know, but it's just determinant of A is what I'll call it right now. So because we swapped rows to get from here to here, the determinant of this matrix should be the opposite of the determinant of A, so opposite in sign. Yep. Now here, these types of row operations that I'm doing do not affect the determinant. Okay. So from here to here, these matrices will have the same determinant then, okay? So the third matrix has a determinant which is also opposite the original. Now to go from here to here, we multiply the row by -1/2. So determinant is going to be multiplied by that amount as well. So determinant of the new matrix is -1/2 of this one. So the negatives will cancel. So it's just half the determinant of A right now. Okay. And then lastly, this type of row operation, again, has no effect on determinant. So at the end, this matrix, its determinant should be 1/2 of the determinant of A. Okay. Now, on the other hand, though, as a triangular matrix, we know its determinant is the product of its diagonal entries. So it should be 1 times 1 times 7. Okay. So we can solve for the determinant of A just by multiplying both sides by 2. So therefore, determinant of A in this example is going to be 2 times 7, so it's going to be 14. Okay? All right. Okay. So especially for larger matrices, it'll be useful to do some row operations on it in order to compute its determinant more quickly. Okay? I would say for 2 by 2 and especially, well, 3 by 3 and especially 2 by 2, you can, but it doesn't necessarily save you that much time, I would say. Okay? All right. Now I want to discuss yet another way of computing determinants. Okay? So this method of computing determinants is often called something like a cofactor expansion. This is probably how I usually compute the determinant of, say, like a 3 by 3 matrix, as opposed to like using the big formula or performing operations on it. All right, so to go over this method, I'll need to again introduce like some terminology or notation. So let's say that we have some matrix A. So we define the ij cofactor of the matrix A to be equal to -1 raised to a power of I plus j times the determinant of the matrix that we get when we remove the ith row and the jth column of A. Okay. Okay. Now we have kind of 2 ways, I guess, of computing the determinant in terms of cofactors. Okay. So you can compute the determinant of A by doing what we call cofactor expansion along any of its rows. You can also do it along any of its columns as well. Okay. So if you do cofactor expansion along the ith row, basically what this method is, it computes the determinant of A by taking each of the entries in the ith row of A. Okay. So yeah, take each entry in the ith row of A, and then you're going to multiply it by its corresponding cofactor. Okay. And then if you add all of those products up, that will result in the determinant of A. Okay. So that's kind of a description in words on how it works. As a formula, it would maybe look something like this. So take each entry in the ith row. So like AI1 is like the first entry in the ith row. You'll multiply by its corresponding cofactor, so like the I1 cofactor. And then again, I take the second entry in the ith row, multiplied by its corresponding cofactor. Keep doing that for every entry in the ith row. You add all of that up, and that's going to give you the determinant, okay? You can also do cofactor expansion along any of the columns, okay? So it's similar, so I'll just kind of write it out real quick. You'll take each entry in the jth column. So like this is the first entry in the jth column. You multiply by its corresponding cofactor. Do the same for every other entry in the jth column down to the nth one. And when you add all that up, it will also give you the determinant. Okay. So I'll illustrate this with an example. I'm going to use the example that we had in the previous, well, the matrix that we had in the previous example. Okay. So we computed the determinant of this matrix, and it was 14. Okay. So we'll just kind of make a note of that. But now I'm going to compute the determinant using this other method, cofactor expansion. We'll see how it works, and it should also give us an answer of 14 as well, okay? Oh, so I'll say one thing first about the formula for cofactor. So you have this -1 to a power of I plus j as part of the formula for the cofactor. So that's going to be like a +1 or -1, depending on I and j. Okay. So that's kind of like a visual that you can use to determine whether it should be +1 or -1. So I'll kind of draw the visual down here. So if you start with like a plus sign in like the first entry of your matrix, and then if you just like alternate in sign along the first row and first column like that, and then continue alternating in sign along each of the rows, that kind of tells you whether -1 to the I plus j will be plus or minus, depending on like your I and your j, okay? So usually I'm not thinking like what's I, what's j, if I add them, what is that? I'm usually just thinking like, okay, I have this visual in my mind, so I know it's going to be plus or minus because I'm looking at this entry, okay? Yes. Yeah, to the power of I plus j, yeah. So let's see how that works in this example. So we can do cofactor expansion along any row or any column. So I'll do maybe at least one row and at least one column to see how it works, okay? So I'll start by doing cofactor expansion along the first row of this matrix. So that means I'm going to take each entry in the first row, starting with the 3. and I want to multiply it by its corresponding cofactor. Now, for the first entry, the cofactor, this is going to be a +1. Okay, so maybe I'll put like a plus in front just to emphasize that. And then I need the determinant of the matrix when I remove the first row and the first column. Okay, so I took the first entry to 3. Then I'm going to remove the first row and the first column. I have this remaining 2 by 2 matrix when I do that, which I'll record right now. And I need the determinant of this matrix here, okay? So I'll come back to that one in a bit, but next, continuing along the first row, the next number that we have is -2. Okay. Yes, Yeah, so essentially I cross out the first row and the first column, and I have 0, -1, 3, 2 remaining. Okay. Okay, all right. So yeah, each time for the cofactors, you have to cross out like a row and a column. Yeah, that's right. Yeah, okay. So like when I move to this entry for the -2, so I will cross out the first row and the second column now. Okay. And that's gonna leave me with this and that. Okay. So let me write those numbers down first. Okay. Now also for the sign here, for this second entry, there's also a minus sign in front as well for the cofactor. That's right. So it'll kind of be like, I guess I'll write it here to emphasize, but it's like -2 from the matrix, and then times the negative of this determinant because the cofactor has a minus sign in it, okay? So it'll be like a +2 in the end, okay? And then next I'm gonna go to the last entry in the first row, which is a 1. And now I'm gonna cross out the row and the column containing that entry, okay? And that leaves you with this 2 by 2 matrix. Okay, and then each of these are 2 by 2 matrices, so we can calculate their determinants by doing the AD minus BC formula, okay? So for this matrix here, its determinant is going to be 0 minus a -3. Okay. Next, we're going to have a +2. And then I'm going to do AD minus BC. Okay. And then lastly, we have +1 times, and then again, if we do the AD minus BC, okay, we'll multiply and add everything up. It's going to be 9 plus 2 plus 3. So that gets us the answer of 14, which is what we found earlier as well, okay? All right. And then just to get some more practice, let's do this again, but using a different row or a different column, okay? So this time, let's choose a column. I'll do the second column, okay? That's right, yes, okay? Yeah, so any row or any column will give you the same answer in the end. So let's see what happens if I do it along the second column. Okay. So I'm going to start with the first entry in the second column then, which is the -2. I need to multiply by its cofactor next. So the cofactor will give us another minus sign. Okay. And then I'm just going to cross out the row and the column containing that -2. And then we have that 2 by 2 matrix there. Okay. So then next I would take the next entry in the second column, which is a 0. And I'd multiply by like its corresponding cofactor, but it's just going to be 0, okay? Because I'm going to be multiplying by 0 in the end. Okay, so normally you'd cross out the row in the column containing the 0, and you'd have this 2 by 2 remaining. But we don't have to worry about that because we're going to be multiplying by 0. So then I'll take the last entry in the second column, which is the 3. That entry gives us an extra minus from the cofactor. Okay. And then I'm going to cross out the row and the column containing that 3. That leaves me with 3, 1, 1 minus 1. Okay? Yes. Uh-huh. Which one? Mm-hmm. Oh, this? This? Oh. Well, this is telling you whether like -1 to the I plus j will be +1 or -1. Yeah, okay. So like when ij is 1, 1, it's positive. So here it's like when I is 1, j is 2, it'll be negative, and so forth. Right, okay. Yeah, so usually I have this kind of visual, and I'm usually using this to determine whether it's plus or minus, instead of like actually thinking like I plus j equals, yeah, that's right, yeah, okay. Okay. So then let's go ahead and work these out real quick. So here this is +2. And then for this 2 by 2 determinant, it's 2 minus 1. Okay. And then next we've got this -3 at the end. And then for this determinant, it's going to be -3 minus 1. So that'll be -4. Okay. And then you get 2 plus 12, so you're going to get 14 again. Okay. All right. So I'm a little bit over time, so I'll just kind of say a couple more things. If you guys have to leave, that's fine. But I'll say a couple more things for the recording. I'm not going to work it out, but just to illustrate, you can do this for larger matrices as well. So I'll just kind of let you see what it looks like for a 4x4 real quick, but I definitely won't be working it out. I'll just make up some numbers for this. Okay, so it's kind of randomly made up this matrix. So let's say we wanted to compute the determinant using cofactor expansion again. So here you might have noticed in the previous example that choosing a row or a column with zeros in it will make your work a little bit easier. Okay. So it's always best to choose a row or a column that has the most number of zeros in it. In this case, then, if I were to do cofactor expansion, I'd want to do it along the third column, okay? All right, because that one has the most number of zeros in it. So here, if I set up kind of like the sign, picture, if you will, I'm going to be using the third column in particular, so we're going to be following this pattern. Okay. Now the first two are going to be 0, so I don't have to worry about the first twos. So starting with the third entry here, we have a 1. And then what I have to do here is, cofactor will be plus, not minus. And then if I cross out the row and the column containing that 1, we're left with like a 3 by 3 matrix now. Okay. All right. And then at the end, we'll have a minus and a 2. And then if I cross out the row and the column containing that 2, we have this remaining 3 by 3. So for a 4 by 4, when you use cofactor expansion, you're going to break it up into like a bunch of 3 by 3 determinants. Yeah. Yes,
Like for the -2, it's just like +2 and then
the minus came from the cofactor, if you will. That's right, yeah. That's right, yeah, that's right, okay. Yeah, good, okay. So then here, to compute these 3 by 3 determinants, you might have to do cofactor expansion again for each of them, for instance, okay? So cofactor expansion is also not really fun once you get to like 4 by 4 or higher, okay? So 3 by 3, I think it's simple enough still, but 4 by 4 or higher, I probably will do some row operations to simplify it a little bit first, okay? Okay. Let me end the review with just some properties of determinants, like additional properties of them. So this first property, I mentioned it earlier, that the determinant of A transpose is the same as the determinant of A. Okay. Let's say that you're multiplying a matrix by a scalar, and you want the determinant of that. Okay. Okay, so earlier we talked about how when you multiply one of the rows by k, the determinant gets multiplied by k as well. Now, when you multiply the whole matrix by k, that's kind of like multiplying all n of its rows by k then. So that ends up multiplying by k like n times. So you kind of get like a factor of k to the n when you do that. So it'll be k to the n times the determinant of A for an n by n matrix A. Okay. All right. Now maybe one of the more surprising properties is that the determinant of a product, A times B, is equal to the product of the determinants, determinant A times determinant B. Okay. So if you maybe imagine how matrix multiplication works, and then you imagine how computing determinant works, it might be surprising that these two are the same. Okay. Lastly, well, maybe not lastly, but now as a sort of consequence of the third property, determinant of like A to a power, like A squared or something like that, will be the same as a determinant of A to the power k. Okay. This last property holds whenever k is like a non-negative number. For k equals 0, we would interpret A to the 0 as an identity matrix, kind of like how a number to the 0 is 1. All right. This formula also works for negative integers if A is invertible. Okay. So in particular, if A is invertible, then the determinant of its inverse will be the determinant of A to a power of -1. or you can rewrite it as 1 over the determinant of A. Okay? And I'll also mention a comment on this as well. So it's a fact that a matrix will be invertible if and only if its determinant is non-zero. Okay. So equivalently, you can say like a matrix is not invertible if and only if its determinant is 0. Okay. And this will come into play when we talk about eigenvalues and eigenvectors, which we'll probably at least start talking about a little bit next time. Yeah, next week is the break, right? Yeah, I guess there would not be a review next week. I mean, I'm still working, so maybe I'll record one anyways. I don't know, we'll see, okay? Staff, yeah, staff doesn't get that Monday, Tuesday, Wednesday off technically, unless we like use our vacation or whatever. So technically, I am working on Monday if I don't take vacation. So I could maybe still record something. I'll see if I decide to do that or not, though. Okay. If and only if. Yeah. Okay. So this fact in particular comes into play when we talk about eigenvalues and eigenvectors. This last one. In a sense, we're actually covering determinants right now. Only because we needed this to talk about eigenvalues and eigenvectors next. Okay. But I'll end the review with that for today because I'm quite a bit over, so I should end it now. Okay. All right. Any questions?